I am Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Synopsys with Madhumita Sanyal. We're going to talk today about DSP techniques for high-speed SerDes. Madhumita, we have so much data that's coming out from all the sensors. Data is being produced everywhere. It needs to be moved throughout a system. How is that changing the landscape of SerDes and all the other technologies that have to deal with all this data?
So basically now we are dealing with, zettabytes of data. So the projection till 2025 is 175 zettabytes of data, which means 21 zeros after one. So we have to handle that amount of data, compute it in our compute system, and then be able to process it and transport it from the compute platform to outside world to the network. So what that means for the SoCs and also the SerDes is basically now your beachfront or the reticle size is limited, right? For let's say 5 nanometer or 3 nanometer technology. Hence, since you have to optimize the beachfront, now the SerDes per lane speed needs to go exponentially, it has to increase. So that's what we see, like going from 800 gig Ethernet to 1.6 terabyte Ethernet. It basically comes down to SerDes per lane speed to be 50 gig per lane to 100 gig per lane to 224 gig per lane. And for PCIe, it is transitioning from 32 gig PCIe 5 to 64 Gbps for PCI Gen 6, and now we are even talking about Gen 7, which is 128 Gbps.
Well, let's take a closer look.
Sure.
Madhumita, what are we looking at?
So here, Ed, we are looking at the modulation techniques of the data, energy, which was valid till 50 gig energy land, and then it moved to the PAM4 land. So we are looking at basically the modulation techniques here.
Madhumita, what's the advantage of moving from NRZ, which is non-return to zero, to PAM4, which is the pulse amplitude modulation?
So as you can see here, we are showing basically the energy modulation. So you have two voltage levels here, 0 and 1. And in this case, in one MUI, which is where the signal is transitioning from 0 to 1, you are transmitting 1 bit per MUI, right? So that was energy. And in PAM4 case, so what happens in energy case, if you have to move to, let's say, 32 gig PCIe 5 was energy, and then you have to move to 64 gigabits per second, which is Gen 6. In that case, if you have to go to 56 or 64 gigabits per second, you basically have to double your Nyquist, right? So energy 32 gigabits per second, the Nyquist was 14 gig, and then for 64 Gbps it will be again 28. So in that case, you have to also, your insertion loss is going to also double. It can go till 70 dB, and in current connector PCB world, that's not feasible, right? That's not something we can compensate for. So that's why we moved to PAM4. Now in PAM4, the swing is same, but as you can see, you have 4 voltage levels here, and in one of these MUIs, previously you were transmitting 1 bit, now you are transmitting 2 bits per MUI. So 0001, 1011, that is what you are transmitting with respect to these 4 voltage levels, right? So now your bandwidth has increased twice.
How do these voltage levels translate into the eyes that most people are familiar with?
Right. So for energy, if you see here, it was like one eye, right? So, and then when you move to PAM4, this one eye is now distributed in 3 eyes with the same swing. So now the swing here is 1/3 of what you saw in energy case. So this is all 1/3. So all this is really good. Like you now can transmit twice the bandwidth with the same Nyquist for Gen 6.
And the whole goal here is to keep those eyes open, right? So that data can move through that.
Right. So the whole concept here is to, you have to make sure that your eye is open enough, which means that on the received side of the link, you have to have enough equalization techniques built into your SerDes so that you are able to, compensate for the channel impairments and ISI, and of course the frequency dependent loss of the channel.
And when you keep these eyes open, that ensures to some extent some data integrity too, right? It means that the data is going to flow through there unimpeded.
That's correct. So what that means is basically when you are transmitting from one side of the link through the channel to the other side of the link, you are able to recover the data what you have transmitted and able to make sure that you recover the data completely and be able to equalize it, and your eye is wide open.
Do those eyes close up over time?
Yes, they can, and that's why we have the DSP techniques. Of course, for PAM4, we need the APC forward error correction to make sure that you can your bit error rate is basically you are error free. So with PAM4, we have introduced the new concept called bit error rate, and before the prefect, before basically the forward error correction, you will have a certain amount of BER, which different standards have a different spec. For example, PCIe Gen 6 have 1E-6 as the spec, and then for Ethernet it is 1E-4 for 100 Gbps. So that's where this forward error correction, although it has this latency aspect of it, but it is able to clear out that error in the system.
Where do DSPs fit into this?
Right. So as we spoke, right, with PAM4, we have more signal integrity challenges because the channel, it's high speed, and you have the channel impairments, the frequency dependent loss is getting higher, as well as you have the ISI inter-symbol interference from the channel when your data is basically traversing from your transmitter of one link throughout the channel to the receiver side of the link. And so DSP is part of the equalization that has to be inbuilt in the SerDes. So you have what you have here is on the transmit side, you would have one kind of equalization, which is basically your transmit FIR, finite impulse response circuit. And what it has is basically it consists of several taps, and it operates in discrete time domain, and you can optimize the value of these tap coefficients, and you can boost the amplitude of the signal so that it can have enough equalization to traverse through the channel and go to the other side.
And with DSP, you have some programmability built in there too, right?
Yeah. So I was just mentioning the transmit side of it. So you have this tap coefficients, the coefficients I'm showing here, it can be for PAM4, it can be 4-tap filter, or you can have 5 taps, and you would be able to optimize that for that given channel. And of course, going to the receiver side, the DSP actually is in the receiver side of the link. So if we go, if we look at each of these blocks on the receiver side, first is this analog front end, and in analog front end you actually have so basically this DSP, you can think of it as like one part is analog and the other part is digital, right? So in the analog part, what we have here in the analog front end, there is passive equalization and there is active equalization. So in case of passive equalization, you can have a termination circuit here. So basically it's a RC network which is chosen to provide the passive equalization, a high pass termination of this circuit. And then it goes to, you can have a CTLE here, which is continuous time linear equalizer. So that is a high frequency component which will allow basically all the providing the channel response in it's attenuating the low frequency and then boosting the high frequency signal, and that's how it's able to operate in continuous time and is designed to provide a linear equalization on the this is all part of the analog circuit.
Typically, though, when you deal with a lot of these designs, the analog guys are completely different than the digital guys. They think
Right.
differently. The signals are different. You're pulling them together here. Do you now need more teams? Do the tools cover all this stuff and make it easier? How does this all work?
Correct. So previously it was all in the analog domain. Now we are moving to this digital domain. So the benefit that it has is basically it's very hard to fine tune these analog circuits with the PBTs, right? So, but with digital, now with shrinking process nodes, you can optimize it further with, the process technologies available, as well as you have the tools, the EDA tools available, which can squeeze the, you can basically optimize the power area, performance, as well as latency of the digital circuit.
Because a lot of these designs are also multi-die, you've got a lot of different pieces coming in. You now can develop this at whatever process node makes sense too, right, and integrate it into a multi-die type of or chiplet type of approach.
Correct. So this basically having it in digital will enable the system implementers to have it in a IO die and be able to reuse it, right? So that is very consistent with the multi-die methodology.
When you think about this, do you also have to think about the package that this is going into? Because a lot of the stuff is now going to be packaged together with other stuff.
Right, of course. So with this high speed, from 6400 or 200, the package, PCB, everything needs to be co-designed along with when you are designing your SoC. So that has to be from the beginning of your SoC design, you need to re-architect your package constraints and look at the bump map of the IPs, and then you have to basically route those signals through the bit front and optimize the spacing between your SerDes or your several macros. And then you have to also go to, you have to use advanced tools like ANSYS and HFSS simulation, and make sure that the signal integrity as well as power integrity, you might have a lot of power domains in here. I want to optimize power. So for example, PCIe will have, even now it has the previously it has the power management, now it has the L0P states where you can dynamically, shut down some of the lanes and still maintain the traffic in mission mode. So all of this power and, power modes, you can perform the power integrity simulation and make sure that everything, your package, PCB and SoC is consistently meeting the spec.
So in a mixed signal environment, which is really what this is, you've got a lot of noise. How do you deal with that? And what kinds of things can you do? I mean, one of the techniques that we've been hearing about is the maximum likelihood sequence detection, or MLSD. What is that? How does that apply here?
Right. So we talked about the conventional DSP, which is your feed-forward equalizer and your decision feedback equalizer. So with the feed-forward equalizer, you kind of clean out the inter-symbol interference, and then with the DFE, decision feedback equalizer, you completely remove that ISI. What MLSD does is it's basically a separate data path right after your FFE, which is feed forward equalizer, and then it's what instead of completely removing the ISI from the data, what it's doing is it's not seeing ISI as a noise or it's just thinking ISI as like it's depending on the transmitted sequence, and it's trying to leverage the energy from the ISI and boost the signals. And basically in here in this space, what I'm showing here is basically your encoded response at the receiver, and which is nothing but your transmitted sequence plus coefficient times the previous transmitted sequence plus the noise, right? So, and if you think of like 16 of these data sequence that's coming from your transmitter, this encoding is being followed for each of these data patterns. And what MLSD, which is the minimum likelihood sequence detector, would do, it would compute compute the Euclidean distance between this sequence versus the encoded sequence and choose the minimum distance from the actual received data versus what the transmitted without any ISI, the transmitted data pattern. So that's where it will choose the minimum distance from all of these different sequence of patterns. Similarly, what happens is, this is a lot of computation, right, with MLSD. So you have to kind of optimize that computation, and that's where there is this Viterbi algorithm that's found to be the most efficient one.
To some extent, what you're doing here is making a lot of trade-offs, right?
Right, right. So we basically, when you have a larger channel, lot of noise, you have discontinuities in the channel, then you would use using these advanced DSP techniques. And with MLSD, you have to remember that you need more area, more power, and it will add little bit more latency. So if you have different kind of channel in your system, so you might want to remove some of the taps from your conventional FFE, as well as you can also shut down the MLSD when it's not required.
If you're moving from PAM4 to PAM6 and eventually PAM7, do you necessarily have that much more speed, and are you dealing with things like, okay, now the noise it's even more susceptible to noise than it was in the past?
Yes, so then the analog front end has to be, the bandwidth has to be able to compensate for that, different modulation, because your eyes are getting even smaller, right? Yeah, and of course, different kind of DSP would be necessary for that.
Madhumita Sanyal, thanks for a great explanation.
Thank you, Ed. Thank you for having me here.